Welcome back. We had spent 2 episodes installing the geometry of multivariable calculus, coordinates, surfaces, vectors, dot and cross products. Today, analysis returns. We redefine the most fundamental object in calculus, the limit, for functions of more than one variable. In one dimension, the limit of f of x as x approaches a is a tidy 2-sided affair. There are exactly 2 ways to sneak up on the number a on the real line, from the left and from the right. If the function settles to the same value L both ways, the limit exists. If it settles to 2 different values, it doesn't. End of story. Today, the story stops being tidy. In the plane, a point A, B has infinitely many directions of approach and infinitely many paths along each direction. The definition of the limit stays the same in spirit. F must approach a single value, L, but it now demands path independence over an infinite family of approaches. This changes the techniques. It is much easier to show a multivariable limit fails than to show it exists. We'll see why, starting with the definition. Here is the definition. We say the limit, as the point xy approaches a, b of f of xy equals L, if f of xy gets arbitrarily close to L as the point xy gets close to a, b, and crucially, in any way possible. Made formal, for every error tolerance epsilon greater than 0, there is a closeness threshold delta greater than 0, such that whenever the point xy is within Euclidean distance delta of a, b, t, but not equal to it, the value f of xy lies within epsilon of L. The Euclidean distance is just the square root of x minus a squared plus y minus b squared, the magnitude of the displacement vector from a, b to xy. Notice the geometry. Within delta of a, b carves out a tiny disk around a, b. The definition demands that for points in this disk, not just points along a particular line, but all of them, the function value stays trapped within an epsilon band around L. The key phrase, the one to underline twice, is in any way possible. Lines, curves, spirals, paths that wiggle back and forth, paths that approach and then retreat and then approach again. If any one of them gives a different value, the limit fails. The wrinkle. Compare what we mean by approach in one dimension versus 2. In one dimension, at a point A on the real line, you can approach from the left, meaning through values less than A, or from the right, meaning through values greater than A. That's it. 2 paths. If both one-sided limits exist and are equal, the two-sided limit exists. In 2 dimensions, at a point A, B in the plane, things explode. You can approach along the line y equals b, the line x equals a, the diagonal where y minus b equals x minus a, and more generally any line through AB of which there is a whole continuum parametrized by slope. But you are not restricted to lines. You can approach along a parabola where y minus b equals x minus a squared, along a cubic, along a logarithmic curve, along a spiral that winds around a, b as it converges. Any continuous curve ending at a, b is fair game. The consequence is asymmetric. To disprove a limit, you only need to exhibit 2 specific paths that disagree. To prove a limit, you have to show that every path, of which there are uncountably many, gives the same value. This asymmetry is why the rest of today is mostly about the proving side. Here is the practical disprove technique. Suppose, for contradiction, that the limit equals some number L. Then by the definition, for any continuous path ending at AB, the values of f along that path must converge to L. That's the forward direction. If the limit exists, all paths agree. The contrapositive is the test. If you can find 2 paths giving 2 different answers, then the limit cannot exist. The limit doesn't care which 2 paths. Any disagreement at all is a fatal proof of non-existence. Strategy: try the cheap paths first. At the origin, the easiest substitutions are the coordinate axes. Set y equals 0, see what f does as x approaches 0. Set x equals 0, see what f does as y approaches 0. If those already disagree, you're done. If not, try the diagonal y equals x. If still stalemate, try general lines y equals mx for a parameter. If those all agree, try parabolas y equals mx squared or x equals mx squared. The pattern: keep widening your family of approach curves. If you find disagreement at any stage, the limit doesn't exist. If everything keeps agreeing, you should start suspecting the limit does exist and switch tactics. The classic example. Let f of x, y equal xy divided by x squared plus y squared, defined for every point except the origin. What happens as the point xy approaches the origin? Path 1, approach along the x-axis, meaning hold y at 0, substituting f of x 0 equals x times 0 over x squared plus 0, which is 0. So along this path, f is identically 0, and the limit is 0. Path 2, approach along the line y equals x, diagonally toward the origin. Substituting f of x, x equals x times x, over x squared plus x squared, which is x squared over 2x squared, which is 1/2. So along this path, f is identically 1/2, and the limit is 1/2. 2 paths, 2 different answers. By the two-path test, the limit as the point xy approaches the origin of xy over x squared plus y squared does not exist, and it's even worse than two paths disagreeing. Try a general line y equals mx. Substitute f of x, mx equals x times mx, over x squared plus m squared x squared, which is mx squared over the quantity 1 plus m squared, times x squared, which simplifies to m over 1 plus m squared. Every slope m gives a different constant value. The function has a different limit along every line through the origin. There is no way to assign a single number to the limit. The surface, near the origin, has a whole spectrum of plateaus radiating out, and which plateau you land on depends entirely on the direction you came from. Here is the geometry on a flat canvas. 3 different approach paths all converge on the origin: the blue x-axis, y equals 0, the red diagonal line, y equals x, and the teal parabola, y equals x squared. The dots along each curve mark a sequence of points marching steadily toward the origin. For our function xy over x squared plus y squared, compute the value at each dot. Along the blue x-axis, every dot has y equals 0, so the function is 0 everywhere on that curve. Along the red diagonal, every dot satisfies y equals x, so the function is identically 1/2. Along the teal parabola, y equals x squared, the function works out to x times x squared over x squared plus x to the 4th, which is x over 1 plus x squared, which also tends to 0. So 3 colors, 3 different sequences of values, the set containing 0, the set containing 1/2, and the set containing 0. The blue and teal limits both give 0, agreement. But the red diagonal disagrees, contributing 1/2. One disagreement anywhere is enough. That is the visual content of the two-path test. Pick paths, evaluate along them, look for disagreement, and if you find it, the limit is dead. So how do you prove a multivariable limit exists? 3 techniques. First, polar coordinates. The substitution x equals r cosine theta, y equals r sine theta converts approach to the origin into the single variable condition r approaches 0. The angular variable theta encodes the direction of approach. If, after substituting, the resulting expression tends to a single value L as r approaches 0, and the convergence is uniform in theta, meaning the bound on the error doesn't depend on which direction you came from, the limit is L. The magic of polar coordinates is that all directions get rolled into the single angular parameter. Second, the squeeze theorem. The same idea as in one variable. Trap the absolute value of f of x y minus L between 0 and some function g of x y that you already know goes to 0. Then f has no choice but to converge to L. Third, and most fundamental, epsilon delta. Start from the definition and produce, given any epsilon, an explicit delta that works. This is the slowest method, but sometimes the only one that fits a hard case. One critical warning: showing that the limit along every straight line through the origin agrees is not enough to prove the limit exists. There exist functions whose line limits are identical, but whose parabola limits disagree. We'll see one in a moment. Lines are a useful first test, but a poor proof of existence. A textbook limit exists problem. Let f of x, y equal the quantity x squared plus y squared times the sine of 1 over x squared plus y squared, defined everywhere except the origin. The inner argument, 1 over x squared plus y squared, blows up to infinity as the point xy approaches the origin, so the sign oscillates wildly. But the outer factor x squared plus y squared tends to 0. Does the product settle? Let r squared equal x squared plus y squared. The function becomes r squared times the sine of 1 over r squared. Now we are essentially in one variable. The direction theta doesn't appear at all, which already is a strong hint. The limit will be path independent. Apply the standard bound on sine. For all real arguments, the absolute value of sine is less than or equal to 1. Therefore, the absolute value of f of xy equals r squared times the absolute value of the sine of 1 over r squared, which is less than or equal to r squared, which is x squared plus y squared. The bound r squared depends only on the distance from the origin, not the direction. As r approaches 0, that bound goes to 0 uniformly. By the squeeze theorem, the absolute value of f of xy is sandwiched between 0 and something tending to 0, so f itself tends to 0. Conclusion: the limit exists and equals 0. The wild oscillation of the sign is tamed by the vanishing of the outer r squared factor. The polar substitution made the path independence transparent. The bound made the squeeze precise. Subtler example. Let f of x, y equal x squared y over x squared plus y squared at the origin. This looks cousin to the failing example xy over x squared plus y squared, but the extra factor of x in the numerator changes the behavior. Start with the cheap tests. Along the line, y equals mx, substitute and simplify. f of x, mx equals x squared times mx over x squared plus m squared x squared, which is mx over 1 plus m squared. As x approaches 0, this tends to 0 regardless of m, so every line through the origin gives limit 0. Encouraging, but we warned earlier, not yet proof. Try parabolas. Along y equals mx squared, f of x mx squared equals x squared times mx squared over x squared plus m squared x to the fourth, which is mx squared over 1 plus m squared x squared. As x approaches 0, also tends to 0. Parabolas agree. Now actually prove it with polar coordinates. Substitute x equals r cosine theta, y equals r sine theta. The numerator x squared y equals r cubed times cosine squared theta times sine theta. The denominator x squared plus y squared equals r squared, so f equals r times cosine squared theta times sine theta. The angular factor cosine squared theta sine theta is bounded in absolute value by 1 for every theta, so the absolute value of f is less than or equal to r. As r approaches 0, the bound to r goes to 0 uniformly in theta. Squeeze theorem, the limit exists and equals 0. Moral, lines plus parabolas suggest the limit is 0, but polar coordinates are what prove it because they handle every direction at once. Why did we have to go beyond lines in the last example? Because lines alone really aren't enough. Here is the counterexample that proves it. Consider g of x, y equals x squared y over x to the fourth plus y squared. Along any straight line y equals mx, compute g of x mx equals x squared times mx over x to the fourth plus m squared x squared, which is mx cubed over x squared, times the quantity x squared plus m squared, which is mx over x squared plus m squared. As x approaches 0, this tends to 0 for every slope m, including the vertical line x equals 0, which gives identically 0, so every line through the origin contributes 0. Now try the parabola y equals x squared. Substitute g of x squared equals x squared times x squared over x to the fourth plus x to the fourth, which is x to the fourth over 2x to the fourth, which is 1/2. Along this particular parabola, g is identically 1/2. Lines, all 0. One parabola, identically 1/2. The two-path test, in the form all lines versus a particular parabola, kills the limit. G has no limit at the origin. This is the cautionary moral. Along every straight line, the limit agrees is a necessary condition, but never a sufficient one. There are always stranger paths, parabolas, cubics, logarithms, that may break the agreement. To prove a limit, switch to polar coordinates or squeeze. With limits in hand, continuity is a one-liner. A function f of two variables is continuous at the point a, b if the limit as the point xy approaches a b of f of xy equals f of a b. Three conditions packed into that single equation, f of a, b must be defined, the limit must exist, and the two must be equal. If anyone fails, f is discontinuous at a, b. F is continuous on a region D if it's continuous at every point of D. Most of the time, continuity is easy in the same way it was in single variable calculus. The building block functions are continuous, and continuity is preserved under sums, products, quotients with non-zero denominator, and compositions. Specifically, every polynomial in x and y is continuous on the entire plane. Every rational function, p of xy over q of xy, is continuous wherever the denominator doesn't vanish. Sine, cosine, the exponential, and the logarithm applied to continuous expressions stay continuous on their natural domains, and compositions of continuous functions are continuous. So f of x, y equals e to the xy, times the sine of x squared plus y, is continuous everywhere, no work required. The hard cases, the ones requiring the techniques of this episode, are the points where a denominator vanishes and the function is undefined, like the origin in our worked examples. There you have to investigate whether the function can be extended continuously by filling in a value, which is exactly the question, does the limit exist? Same trichotomy as in single variable calculus, now for two variables. Take our three worked examples. All three were undefined at the origin because the denominator was 0 there. In each case, we asked whether the limit existed. For xy over x squared plus y squared, the limit did not exist. Different paths gave different values. No assignment of f at 0, 0 can patch this. The discontinuity is essential, an irreparable hole in the function. For the quantity x squared plus y squared times the sine of 1 over x squared plus y squared, the limit was 0. If we extend the function by defining f at 0, 0 to be 0, the function becomes continuous on the whole plane. The discontinuity is removable. For x squared y over x squared plus y squared, the limit was also 0. Same story, set f at 0, 0 equal to 0, and continuity is restored. Removable. The test for removability is precisely whether the limit exists at the bad point. If it does, plug it in and the function becomes continuous. If it doesn't, you're stuck with a permanent discontinuity. So the entire content of today's episode, existence versus non-existence of multivariable limits, is the test that tells you which singularities can be removed and which cannot. a brief generalization to n variables. The definition is the same. For a function f of an n-dimensional input, the limit as the vector x approaches the vector a of f of the vector x equals L exactly when, for every epsilon greater than 0, there is a delta greater than 0, such that whenever the vector x lies in the punctured ball of radius delta around the vector a, meaning the magnitude of the vector x minus the vector a is greater than 0 and less than delta, the value f of the vector x is within epsilon of L. Geometrically, the disk in two-dimensional space becomes an open ball in three-dimensional space and an open n-ball more generally. The function must approach L from every direction inside that ball. Continuity at the vector a is again limit equals value. For proving existence in three-dimensional space, spherical coordinates play the role polar coordinates played in two variables. Write the vector x as the vector a plus r times the unit vector u, where the vector u is a unit vector and r is the magnitude of the vector x minus the vector a. Then approach is r approaches 0 and the direction u ranges over the unit sphere. A bound on the absolute value of f of the vector x minus L by something depending only on r and not on u proves the limit by the same squeeze. The conceptual point, the difficulty in multivariable limits, scales with dimension via the size of the unit sphere of approach directions. The 0 sphere has 2 points. The 1D case, the 1 sphere has a whole circle. 2D, the 2 sphere, a whole sphere. 3D, more directions, harder limits, same machinery. Recap. The multivariable limit, the limit as the point xy approaches a, b of f of x, y equals L, means f approaches L along every path of approach, not just two, but every continuous curve ending at a, b. The epsilon delta definition packages this into a single condition on a disk around a, b. To disprove a limit, find two paths giving different values. The classic example, xy over x squared plus y squared at the origin, gives 0 along the x-axis and 1/2 along y equals x, so the limit does not exist. To prove a limit, lines aren't enough. Use polar coordinates, x equals r cosine theta, y equals r sine theta, and bound the result independently of theta, or invoke the squeeze theorem with a path-independent majorant, or grind through epsilon delta directly. Example, the quantity x squared plus y squared times the sine of 1 over x squared plus y squared is bounded by r squared, so it squeezes to 0. Example, x squared y over x squared plus y squared in polar form becomes r times cosine squared theta sine theta, bounded by r, so it also tends to 0. Continuity is then a one-liner, the limit as the point xy approaches a, b of f equals f of a, b. Polynomials, rationals where the denominator doesn't vanish, sine, cosine, exponential of continuous expressions and their compositions, all continuous. A discontinuity is removable exactly when a limit exists at the bad point. Next episode, the derivative returns, but only along one axis at a time. That's multivariable limits and continuity. The definition is the same as in one variable in spirit, f approaches L as the input approaches a point, but the path quantifier is different. In any way possible becomes along infinitely many paths. Two-path disagreement disproves a limit. Polar coordinates or a squeeze prove one, lines alone never suffice. If this helped, like, subscribe, drop a comment. As a small challenge, try to decide whether x cubed plus y cubed over x squared plus y squared has a limit at the origin, and if so, what it is. The polar substitution makes the answer very pretty. Next episode, derivatives return to the stage. But with two input variables, the ordinary derivative splits into partial derivatives, one for each input axis, each computed by holding all other variables still and differentiating in one direction. They are easy to compute, but, in a twist we'll meet, the existence of partial derivatives does not imply full-blown differentiability. The path pathologies of today come back to bite. See you there! Today we generalize the limit. For a function f, r squared to r, lim of xy2 of a b f of xy equals L means f approaches L as x, y approaches a, b along every possible path. In one variable there are only two, from the left and from the right. In two variables there are infinitely many, lines of every slope, parabolas, spirals, curves with corners. To disprove a limit, find two paths that give different values. The textbook example is f of xy equals xy x squared plus y squared at the origin. Along y equals arrow, it is identically 0. Along y equals x, it is identically 1, 2, 2. The limit does not exist. To prove a limit, polar coordinates often help. Substitute x equals r cosine theta, y equals r sine theta, and show the r to 0 limit is independent of theta. For x squared plus y squared sine 1, x squared plus y squared, the polar substitution gives r squared sine of 1 y squared, which squeezes to 0. For x squared plus y squared at the origin, every line y equals mx gives every parabola y equals mx squared gives ever, and the polar form r cosine squared theta sine theta is bounded by r and squeezes to 0, so this limit exists and equals 0. Continuity of f at ab means lim of xy, 2 of ab f of xy equals f of ab. Polynomials are continuous, rational functions are continuous where the denominator is non-zero, compositions of continuous functions are continuous. Next episode, the partial derivative, the ordinary derivative along an axis, with all the other variables held still, and how its existence is weaker than full differentiability for exactly the same path reason we learned today. If you got something out of this, please like the video, drop a comment with what clicked for you, or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching, see you in the next one.